It looks like we're recording. So it's my pleasure to welcome Gaetan. He'll talk today about multiplicity-free tensor products for simple algebraic groups.
Thank you. Thank you very much for the invitation. So today I will talk about multiplicity-free tensor product for a simple algebraic group. So I will start by recalling some definitions and introducing the main questions, and then discuss some of the techniques that we use to solve this main question about tensor product of representation. So we fix K an algebraically closed field. And we will denote by P its characteristic. And for the moment, we have no assumption, no specific assumption on the characteristic. And we take G to be simply connected simple linear algebraic group over K. So for example, we can think of G to be SLN K. That's one of the most important examples. Inside this group, we can fix T a maximal torus. So inside SLN, you can just think of the diagonal matrices. And we denote by X the set of characters of T. So map from the torus to our field. Okay. So inside this set of characters, we have a root system, which we will denote it by phi. And sometimes it will be more convenient to consider not only the set of characters, which is a discrete set, it's a lattice, it's isomorphic to z to the power n, but to see it inside a Euclidean space. So we'll just tensor the set of characters with the real numbers in order to have a real vector space. And I will denote this vector space by xr, which is just X tensor product with R. So phi is a root system, and we fix pi a base of this root system, and we denote phi plus the set of positive roots with respect to this choice of a base. Okay, and to complete the picture, we need to introduce the fundamental dominant weight. So the fundamental dominant weights is a set of weights which generates the lattice X. It's not the case of phi when G is simply connected, but we need to introduce another set of generators. And this set, omega 1 up to omega n, is defined by the following relation. We need that omega I with alpha G check is equal to 1 if I is equal to G and 0 else, where alpha G check is 2 times the root alpha G over the square of its norm, and I denote with parentheses the scalar product on this the Euclidean space XR. Okay. So an example, if I take G to be SL3K, so phi is of type A2 according to the classification of Dynkin diagrams. So I have a root system which looks like that. And here I can put alpha 1 and alpha 2. And then the fundamental dominant weights will look a bit like that. Here I have omega 1, and here I have omega 2. And we see that, so alpha 1 is orthogonal to omega 2, and same for alpha 2 with omega 1. And here, the highest root in the root system, alpha 1 plus alpha 2, is also equal to omega 1 plus omega 2. And we say that a weight lambda in X is dominant if lambda is a sum of the fundamental dominant weight with positive coefficient. And we denote by X plus the set of dominant weights. Okay. So one important result in the representation theory of algebraic group is the classification of simple modules for an algebraic group. And by modules, I will always, for me, all the modules are finite dimensional and rationals. And we have this theorem, this classification of simple modules. Which states that we have a bijection between the set of simple G modules and the set of dominant weights. And if I have a dominant weight, I will denote by L of lambda, the simple modules with this corresponding weight. And the weight associated to a simple G module is the highest weight. So when G acts on the module, the torus also acts on the modules. We have a decomposition of the modules with respect to the action of T inside weight spaces. And we have an ordering on the on the weights, which allows us to pick one weight which is the highest one, and this will be the corresponding element in the set of dominant weights. And for example, the natural choice for SL3 will yield. I mean, we need to choose a basis, and there is not only one choice, but the natural choice turn the natural SL3 modules for the matrix multiplication corresponds to L of omega 1. So omega 1, the first fundamental dominant weight. Freeness, so I will introduce now what this means for a module to be multiplicity-free. So we take M, a G module, and we fix a composition series for M. So it's a sequence of submodules such that each submodule is maximal in the next one. So each quotient, mi over mi minus 1, is simple. And so using the classification of simple modules, there exist weights nu1 up to nu s, I mean dominant weights, such that mi over mi minus 1 is isomorphic to L nu I. And we say that M is multiplicity-free if all this composition factor, all the nu I, are distinct. And since I will often use this notion of multiplicity freeness, I will abbreviate it by MF. And another important notions when we study modules for algebraic groups is the notion of a complete reducibility. And so M is completely reducible if it's isomorphic to a direct sum of simple modules. Okay, so now I'm ready to introduce the main questions that we ask ourselves with Jonathan for our paper. So, question. We want to classify the pairs of weights lambda mu in x plus square such that the tensor product of the two corresponding simple modules, L lambda tensor is L of mu, is multiplicity-free or completely reducible. So first, let me say a few words about the case when the characteristic is equal to 0. So first thing, in characteristic 0, all modules are completely reducible. So this question is easy to answer in characteristic 0. And for the question of multiplicity freeness, there is a theorem the theorem of Stanbridge from 2003, which provides a complete classification of pairs of dominant weight such that the tensor product is multiplicity-free, and this is for all types of group. So G can be of type SLN, it can be an SPN, it can be an exceptional of exceptional type. We have a complete classification in all the cases by Stanbridge in 2003. So the characteristic 0 is everything is done. In positive characteristic, well, it's a bit more complicated. So the first thing is we have some non-trivial extension of simple modules. So the category of modules of finite dimensional G modules is not semi-simple. So not all the modules are completely reducible. And for the multiplicity freeness question, it's also a different question than the one in characteristic 0. But we have some results, and that's really the main topic of this talk. So I will start by introducing some more definitions which are related to the case of positive characteristic. And I think that you can no longer see my screen. Can you?
No.
Okay, sorry for that.
We can see it.
Okay, perfect. So one more definition. If we take lambda, which I will express as a sum of fundamental dominant weight, we call lambda p restricted if all the coefficients are strictly smaller than p. And the first important result in the direction of the classification is a reduction theorem, which allows us to consider only the case of dominant weights which are p-restricted. So reduction theorem. So we take lambda, which I will express as lambda 0 plus p times lambda 1 plus and so on until p to the power m. Lambda m, the p-adic expansion of lambda, and same for mu. And so I want that all the lambda i's and the mu i's are p-restricted. Then the tensor product L lambda with L mu is completely reducible if and only if L lambda I tensor product with L mu I is completely reducible for all I. So in order to study all the tensor product, it's sufficient to only consider dominant weights which are p-restricted. And I will not prove this theorem, but I will give some ingredients of the proof.
We have a question. Yeah, sorry, that first, it should be a tensor product at the top two, right? Like L lambda.
Oh yeah, sorry.
Okay, sorry. It's just
Yeah. It's a typo, yeah. So the first ingredient is the Steinberg tensor product theorem. Which says that if I write lambda as if I write the p-adic expansion of lambda, then L of lambda is isomorphic to L of lambda 0 tensor product with the first Frobenius twist of L of lambda 1 tensor product and so on until the mth Frobenius twist of lambda m. So here L mu of I is the eth Frobenius twist, which means that I compose. So I have my representation of G into some GLT, let's say, which corresponds to the weight mu. And here I have the Frobenius endomorphism, and I take its eth power, and then I compose. And this composition corresponds to the modules L mu, to the eth Frobenius twist of the module L mu. So that's the first ingredient of the proof. And the second ingredient of the proof is a theorem by Jonathan Gruber, in 2021, which states that if the tensor product of L lambda and L mu is completely reducible, and we have lambda and mu p restricted, then all the composition factor of this tensor product are also p-restricted. And so if I go back to this theorem, this means that whenever we are completely reducible, here in this expression, all the composition factor will also be p-restricted, and so in some sense we are only considering p-restricted stuff, and we are not going from an element which is just a power of p to the next power. It cannot happen because everything is p-restricted, so we are not adding some powers of p. So that's the main ingredients of the proof. And we have a similar result for multiplicity freeness. So in this theorem, okay, it's not working, sorry. Okay, here in this theorem, here I can put multiplicity-free instead of completely reducible. And same here, multiplicity-free. And then we have the same reduction theorem. So the tensor product of L lambda and L mu is multiplicity-free if and only if all the L lambda I tensor product with L mu I are multiplicity-free. And the last ingredient to prove the theorem for multiplicity freeness is the following result, which is also due to Jonathan Gruber. And which states that if we take lambda and mu two dominant weights, if the tensor product of L lambda and L mu is multiplicity free, then this tensor product is also completely reducible. And so this shows that in positive characteristic, we have a strong connection between the notion of complete reducibility and of multiplicity freeness, at least when we consider of simple models. And so this is also some motivation to consider multiplicity-free tensor product. It's when we know that a tensor product is multiplicity-free, then we automatically know that it is also completely reducible. So we have some information about its structure, only considering the multiplicity free of the multiplicity, sorry, of the composition factors. And one thing which is interesting about this lemma is that we can use it in the classification. We use it really in both directions. So one direction is we have the classification of completely reducible modules, then we can restrict our attention to completely reducible tensor product in order to classify multiplicity-free tensor products. We don't have to, if we know that one tensor product is not completely reducible, then we automatically know that it's not multiplicity-free. But sometimes it's also useful to prove that a tensor product is multiplicity-free in order to prove that it's completely reducible. Sometimes it's easier to prove that it's multiplicity-free. And another important tool that we use for the classification of multiplicity-free tensor product is a link between the characteristic 0 and the positive characteristic. And since we have the classification in characteristic 0, can use all those results in positive characteristics. So this is the following theorem. So we will denote by GC the algebraic group of same type as G, but over the complex number. So for example, if G is SL3 over the algebraic closure of FP, then GC is just SL3C. And similarly, I denote by LC lambda a simple GC module of highest weight lambda. And then, so we take lambda and mu two-dominant way. And if the tensor product of L lambda with L mu is completely reducible, and the tensor product for the group over the complex number is multiplicity-free, then the tensor product in characteristic P case of positive characteristic. And this fact relies on the fact that for the classification in characteristic 0, we are using some combinatorial objects, the Weil characters, which still have some, which also mean something in positive characteristics. We can also use those objects in positive characteristic. Okay. Another important tool for the classification is the so-called alcove geometry, and I will say a few words about that now, and then just show you quickly how the classification works. And I will not state the full classification because it's a big table in our paper, but if you're interested, you can find the paper that we wrote with Jonathan Gruber on the archive, and there you can find all those tables, which some of them are quite big, but it's always the case in algebra with classification, I guess. Okay, so alcove geometry. So as before, P is greater than 0, and I denote by rho the half of the sum of all the positive roots in our root system. And I will also denote by W the Weil group associated to the root system phi. So this is a Coxeter group generated by reflection with respect to the simple roots. And so for beta, a positive root, and m an integer, we define the hyperplane h beta m to be the set of elements in our Euclidean space xr such that the scalar product of x plus rho with beta check is equal to p times m. And definition, an alcove is a connected component of our vector space where we remove all those hyperplane. So this is a bit abstract, but in the case of A2, so we have our root system, and then the alcoves will look a bit like something like that. We have some triangles, and we have those big hyperplanes, and so on and so forth. And so each of this triangle is an alcove, and we have a lot of information about the structure of the models, which is related to the geometry of those alcoves. And for that, I need another definition. So I will define the group W tilde as the group generated by the affine reflection S beta m, where S beta m is the reflection with respect the orthogonal reflection with respect to the hyperplane H beta m. So we have a Coxeter group. So this is a group really generated by reflection. We can find a set of simple reflection generating these groups, and this group will act on our Euclidean space XR, and we have a lot of non-trivial results about the structure of the models and the action of this group. And for example, the linkage principle, which states that if we take lambda and mu in x plus, and so if M is a non-trivial extension of L lambda and of L lambda. I'm writing a tensor product because everything is in tensor product, but it's not the case here. Is a non-trivial extension of L lambda by L mu. Then lambda belongs to the orbit of mu with respect to the action of W tilde. So that's an example of the kind of result that we have. Okay. And one notion that we introduce in our paper is the notion of reflection smallness. So we take again lambda mu two dominant weights, and we say that, okay, maybe I should fix, before that I should fix the alcove, so in which the weight lambda lies. So let's see the alcove with lambda in C, and we say that mu is reflection small with respect to lambda if S dot lambda plus W acting on mu is greater or equal to lambda plus W mu for all elements W in the Weil group and all element S reflection in a hyperplane in the upper closure of C. So what does this mean? If I go back to the picture, okay. So if I take a weight lambda here, and then I take, let's say mu is something somewhere here. So this is the alcove where lambda belongs to. And then if I put lambda plus mu, if I'm still inside the alcove, and same for, let's say that we have lambda plus one element W1 of mu is here. Let's say that lambda plus W2 of mu is here. Then this one will be reflection small because here the two hyperplanes in the upper closure of the alcoves are this one and this one, and we are below those hyperplanes. All the lambda plus mu and lambda plus W of mu are below those hyperplanes. So we cannot cross the hyperplane which are above the alcove, but it's not a problem that we cross the one which is below the alcove. This is not a problem.
I have a question.
Yeah.
Scott. So are you assuming the existence of regular weights, like are you assuming that the prime is larger than the Coxeter number in this setup?
I mean, we can define alcoves in even if it's not the case, but then we have no weights in the alcove. So
That's right.
to use this statement, yes, I assume that we have some regular weights. Exactly.
Okay, good.
And okay, sorry, I think that's, I don't know why, but I think that you cannot see my screen now. I will just connect it again. Sorry for that. So yeah, I assume the existence of regular weights here. I mean, otherwise these statements makes no sense. I mean, here I really assume that lambda is p-regular. But for the classification, then we also have a classification in the case where we have no p-regular weights, but we use other techniques. And so we have some result related to these notions. So take lambda in a dominant weight which belongs to the alcove C, and mu reflection small with respect to lambda. Then first result, the tensor product L of lambda tensor with L mu is completely reducible. And second result, all the composition factors of this tensor product belongs to the upper closure of C. So that means that we can take the wall which are above. So this is also one of the big result that we use in the classification. And I think I have maybe 3 minutes left or something like that. I will just say a few words about the classification in the case of SL3. Just to give you an overview on how we can treat this question. So for SL3, we have two p-restricted alcoves, so which means alcoves which contains p-restricted weights. And as we have seen, we can restrict our attention to alcoves with restricted weights. And first possibility, so I will denote these alcoves by C0, C1. First thing that one can, and we know that all the composition factors also need to be p-restricted if we are interested in completely reducible models, for example. So first thing that one can prove is that if lambda and mu both belongs to C1, then it's not completely reducible. Then, so without loss of generality, we can assume that mu is either in C0. So other possibility, lambda in C1, mu in C0. And then basically the only possibility where we are completely reducible is mu is reflection small. So this is a case which has also been treated. Same here with lambda in C0 and mu in C0 with mu reflection small with respect to lambda. So those are all the easy case. And another result that we use for the classification is that if we take two weights in C0, then we cannot have a composition factor in C1. So that means that if the sum of the two weights is above the hyperplane which crosses here the two alcoves, then it has to be on a wall. And so we can restrict our attention to only a few cases where the sum, for example, is here inside this wall or symmetrically on the other one. And those cases needs to be treated separately. We have not a general techniques for those. And sometimes it's completely reducible and multiplicity-free. And those are the cases where it's interesting to consider the question of whether the tensor product is multiplicity-free, because it's often easier to prove that it's multiplicity-free than to prove that it's completely reducible, because we have some special modules that we consider. And so those are the first case that we consider, and then we also need to consider the weights which are on the wall, so on this wall, but we see that since those weights are pre-restricted, we don't have a lot of choice to keep inside the pre-restricted weights when we add a weight. And then also this wall here, and basically that's how this work, how this classification work. We take a weight in an alcove, we see how so in either C1 or C0 we take mu, and we look where the sum can ends in, and this allows us to treat case by case all the possibilities, and at the end we have a big classification result. And so yeah, sorry, that was a bit quick at the end, but this was just to give a bit of motivation on why we are interested in all this concept that I talk about for the last 50 minutes. So thank you for your attention, and that's it for me.
Questions?
Yeah.
That's a question.
Yeah, so does translation come into play here at all?
Sorry, I didn't hear the questions.
Dan asked if translation comes into play at all.
Sorry, the translation. Sorry, again.
Yeah, Dan wants to know if translation comes into play at all.
Yeah, the translation. Yeah, it's in the proof that if mu is reflection small with respect to lambda, then the tensor product is completely reducible. There we use the translation principle. Yeah.
Okay. Thanks.
And we also use it at some other points in the paper, but yes, this is something that we use.
Yeah, so I guess I'm curious, this result of Jonathan's, that's if you take a tensor product of two simples and it's multiplicity free, then it's automatically completely reducible.
Yeah.
Like, can you say a bit about what goes into that? I mean, that seems kind of amazing to me.
So
Sorry.
I mean, so yeah, this is amazing. So the question is, if I can say some more about the proof, or
Yeah, I guess, or what goes into that? I guess I was sort of surprised by that.
sure. So I will just give an idea, but the idea is that the simple modules are contravariantly self-dual, which is a kind of duality. And if you take the tensor product of two modules which are contravariantly self-dual, then the tensor product is also contravariantly self-dual. And what does that mean? That means, in some sense, when you have a module M, you can write its composition factor. So if it's completely reducible, then all the composition factor are on the same level, and we have no non-trivial extension. And if it's not completely reducible, then we can have, for example, L lambda in top of L mu or something like that. That's the possibility that one can have. And when you are contravariantly self-dual, that means that you have, in some sense, a symmetry. So this one would not be contravariantly self-dual because it's not symmetric, but here, if I add the L of lambda, then it's contravariantly self-dual because you can switch those two and still have the same composition factors. And that's what comes into play for this proof. So if you are contravariantly self-dual, then you have two possibilities. Either you are completely reducible, and then you have all the modules on the same line, and basically anything can happen. You can have multiplicity or not. But if you're not completely reducible and you have a module which appears on top, then it's also need to appear on the bottom, so you are not multiplicity free. And that's the idea of the proof of this result.
Great, thank you.
Do the PRV components play a role in anything, or in the case where things are multiplicity free, do you know anything about the components appearing?
The composition factor, you mean? Sorry. Sorry, I'm not sure that I did understand.
Yeah, so I'm wondering if the PRV components, so at least I'm thinking characteristic 0, if you decompose the tensor products, there's PRV components. Some of the combinatorics you're looking at look familiar. Or yeah, I guess I'm just curious about like if it's multiplicity. If it's multiplicity free, do you anything? No one can you say anything about the composition factors?
I would say yes and no. I mean, it's so in some cases, yes, because we really need to prove that it's I mean, okay, it depends. To prove that it's multiplicity free, sometimes we just use that it's completely reducible and that it's multiplicity free in characteristic 0. And in the paper of Stambridge, there is no, we don't know the decomposition, we just know that it's multiplicity free. So in those cases, we have no explicit decomposition. In some other case, we had to really compute the decomposition. And so, yeah, in those cases, yes, we have. I don't know if it answers your question.
Yeah, thank you. Other questions? If not, let's thank the speaker again.